Hello friends, today we are discussing about the surface tension by Jaeger's method. As we know, the excess of pressure inside an air bubble in a liquid is the pressure is equal to 2T by R, where T is the surface tension of the liquid and R is the radius of the bubble. Jaeger's devised a simple and ingenious method to determine the surface tension of the liquid by measuring the excess of pressure necessary to produce such bubbles. Here is the apparatus of Jaeger's method, and this apparatus is used for this purpose that consists of a wolf bottle is here. In one mouth of bottle, a dropping funnel containing water is fitted in other a glass tube. To this tube, a manometer is connected. Here it is the manometer connected, and the manometer scale is here, which contains a liquid of low density of liquid, so that difference in the levels of the liquid and its limbs may be large for given pressure difference. So upper limb and lower limbs are there. The end of the tube is drawn into fine capillary tube, and top is cut perpendicular to the axis of the tube and the quite smooth, so that there appears no roughness, or there is no appears no roughness even when seen under a microscope. The opening of this tube lies at a depth of 4 to 5 centimeter inside the liquid, of which the surface tension is to be determined. This is the simple apparatus. Now we are discussing the experimental method. Due to the capillary action, some liquid always rises into vertical parts of the tube to a height well above the level of liquid outside it, with its meniscus of spherical shape. The stopcock of the dropping funnel, is slightly open, so that the water falls slowly into the wolf bottle, that resulting to displace, and thus the force of air insert in the tube. Suppose the tube is PQRS. So inserting the tube, the liquid column in the tube RS slowly goes down until it reach at the end S, or end of the capillary tube, and the bubble is formed here, like this one. The bubble is formed there. As the pressure inside the bubble increases, the radius of it gradually decreases. The radius of the bubble acquires minimum value when the bubble when the bubble is of the same diameter as the opening of the capillary tube. At this stage, the pressure inside the bubble acquires a hemispherical shape of radius r equal to that of the orifice S, so that the maximum pressure inside the bubble is noted. With the help of manometer M. During the formation of the bubble, the liquid in one limb of the diameter rise and the maximum difference H in the heights between the two limbs of the manometer is observed. The bubble grows further due to the force of air. Its radius increases, hence the pressure inside it decreases. This results in the disturbance in equilibrium between its internal pressure and constant external pressure. Now the bubble becomes unstable and breaks away. The whole operation is so regulated that it takes about 10 seconds for a single fresh bubble to be formed at the end of the capillary tube. The radius r on the surface on the orifice is measured with the help of microscope. We can easily observe the bubble. So what action takes place is observed by experimental method. So here let the pressure be the atmospheric pressure. Now consider the equilibrium of the bubble just before breaking. So that the pressure inside the bubble is equal to P plus H rho G, where capital H is the maximum difference of the levels, or that is the difference of the levels of the liquid in the manometer, and rho is the density. Then the pressure outside the bubble, that equals to P plus H dg. Here H is the small h is the depth of the orifice below the free surface of the experimental liquid, and d is its density. So with the help of these two pressure, we can calculate the excess of pressure inside the bubble, that is H rho g minus H dg. Here we take the g common, so we get H rho minus H d into g. But as the excess of pressure inside the bubble, that is 2T by R, so we can write this excess of pressure 2T by R is equal to H rho minus Hd into G. And we arrange this T, 2 goes to denominator of this side, so we get T is equal to H rho G minus Hd into Gr by 2. Thus, by knowing the values of various quantities, we can calculate the value of T for given liquid. In Jaeger's method, the bubbles are formed inside the liquid, where the temperature can easily be controlled and measured. Hence, the method can readily be used the study of variation of the surface tension with temperature. If the experimental liquid is heated in the vessel and mercury thermometer is suspended inside the liquid to measure its temperature, the reading of capital H are taken at various temperature, keeping small h as a constant. Now the value of the surface tension at various temperatures can be evaluated easily. A capillary tube of platinum is used to measure the surface tension of the liquid at a high temperature. While performing such experiment, some precautions must be taken, like the whole apparatus must be airtight. The flow of water should be carefully regulated so that the rate of formation of bubble is quite uniform at the jet. The bubble should be formed singly and slowly. This means the bubble should be singly or and slowly. The bore of the capillary tube should be circular and it should be very small, about 0.3 millimeter in a diameter, so that the maximum pressure may be occur in a in a bubble when it is hemispherical. Several observations of two mutually perpendicular diameters must be taken for the diameter of the orifice of the capillary tube. The capillary tube should be clean. The contamination of the surface by the grease changes the value of surface tension. The Jaeger's experiment has some advantages. The first, as the radius of the capillary tube is required at the opening S of the opening at the end of the capillary tube, hence error due to the non-uniformity of the bore are avoided. The liquid air interface is continually renewed due to the bubbles. Hence the errors due to contamination of the surface affecting the surface tension are avoided. The method can also be used for the investigation of variation of surface tension of a solution with concentration of the dissolved substance. By employing suitably capillary jets, surface tension of molten metal may also be determined. The variation of surface tension with temperature can be studied by this method. When the experimental liquid has a finite angle of contact, Jaeger's method, which is independent of the contact angle, gives the true value of surface tension without the interference produced by the contact angle for a glass liquid pair. So with the help of these such experiment, we can find the excess of pressure inside an air bubble in a liquid, that is P is equal to 2T by R, and the by the help of Jaeger's experiment, the surface tension is equal to H rho G minus HD into GR whole divided by 2. So this is the Jaeger's method for the determination of surface tension. Thank you very much for watching this video.